In this section, we're going to discuss how we bring scientific data into Sculpting Viz for visualization. In earlier sections, we discussed how we bring in artifacts used for visualization, glyph geometries, texture maps, line types, and so forth. Now we're discussing the scientific data itself, the underlying data that we're visualizing. Here's the big picture. Data for scientific visualization generally comes from a simulation running on a large-scale parallel server. One such example is WRF, a widely used weather simulation code. From various inputs, including so-called boundary conditions, WRF evolves a model of the weather through time, producing data sets that, for example, tell us the temperature, humidity, wind direction, and velocity everywhere in a region of the atmosphere at a set of points in time. From this raw data, visualization programs run algorithms that produce derived data products which, when rendered to images, allow users to understand the simulation results. Examples include slicing the data and color mapping the results, or placing little arrows periodically to show how the wind flows. You can see such renderings on the Weather channel. Paraview is one such visualization system, capable of taking large-scale simulation data, deriving renderable imagery, and then typically rendering it. Here we will see how we use it instead as a pipeline stage, preparing data for subsequent rendering. Here this rendering is done by ABR, running on a high-powered single computer that is capable of attaining rendering speeds sufficient for virtual reality use. Now let's look at how we create these renderable data products derived from potentially very large raw data and get them into ABR for display. The basic input format is the VTK unstructured grid data type. Unstructured grids consist of two parts, the geometry describing the three-dimensional form of the data, and values that are defined on the geometry. Sculpting Viz uses the term key data for this geometrical information and refers to the values defined on the geometry as variables. We support three basic geometrical forms, all defined in 3-space: surfaces, path lines, and points. These are specified in a VTK unstructured grid as a set of vertices and a set of elements, or cells, that link the vertices together. For example, surfaces are sets of triangles that are defined as lists of IJK triples that list the vertices that comprise each triangle. Similarly, path lines are derived as arbitrary length lists of vertex indices. Points are simply single vertices. Data is defined on the vertices of the data set and interpolated in between. Single values for scalar variables, for example, temperature or humidity, or 3 tuples for vector variables such as wind direction. All will be represented as 32-bit floating point numbers. There are lots of ways to create VTK unstructured grid objects and export them to VTU files. VTK is a C++ class library, and there are bindings for many languages. I use VTK inside Python for a lot of work. However, the most straightforward method of creating VTK unstructured grid datasets is to save them from Paraview as VTU data files. While we can't really teach Paraview here, we can give you an idea of what's going on. Here we see Paraview in action, having imported a weather dataset from WRF. Paraview enables the user to derive renderable data objects from the original input data based on parameters that the user can set. Here the user has used several Paraview filters to create a visualization of the data that consists of surfaces corresponding to clouds, an elevated terrain surface, and some streamlines that show particles as they're carried by the wind, another variable in the dataset. These visualizations are built up of pipelines of Paraview filters. Here we see the Paraview pipeline browser. The pipeline browser shows us the sequence of filters being applied to the data and gives us the means to alter and extend these sequences. Here's a close-up of the pipeline browser showing the 3 sequences of filters being applied to the WRF data. At the top we see the original data imported using file points to open and consisting of a time series of data sets, the variables describing various properties in the atmosphere over the western United States at a set of points in time. Then there are 3 sequences of filters, generating the derived data that you can see in the resulting visualization. The last filter in each pipeline has an open eye, indicating its visibility in the result. And here is the resulting visualization. You can see the three different derived data sets rendered: the lofted terrain surface, the cloud surfaces, and the streamlines. Unfortunately, each of these three pipelines creates as a result as PolyData objects, a much older data type that has been superseded by the unstructured grid data type, which has not been thoroughly expunged from Paraview. We can convert these PolyData objects to unstructured grid objects by simply passing them through the append datasets filter, which we've added here at the end of each of the three sequences. Once we've converted the derived data objects to unstructured grid format, we can write them out to disk. With an append datasets filter selected, use the Save Data button to write the data out. A file browser will appear. Give the output files meaningful names. I used wharfclouds.vtu, wharfstreamlines.vtu, and wharfsurface.vtu. And note the directory where you put them. Now, in that directory, run the vtk2abr.py Python 3 script on them. This will install the data into ABR. Note that this must be done on the system where the ABREngine will run. If the data was generated on another system, it will have to be copied to the ABR host first. Now with the ABREngine running and the ABR GUI up, hit the button that looks like an SD memory card. This will bring up a dialog showing the available datasets. Here at the bottom, we see the three datasets we just imported. Note that the names of these objects comes from the names of the original VTU files. Hit the crosses next to them, and they'll be activated into the list of active key data objects. And here we see them in the key data pane of the ABR GUI, and we can now use the ABR GUI to show them in many, many ways. This process is a bit clumsy, however. We had to create the VTU files in Paraview, we had to write them out, potentially move them to the system hosting ABR, and run Python scripts to install them. We could streamline this by attaching Paraview directly to ABR. Here's my setup at home. On the left is my Mac, where I do almost all my work. On the right is a Windows system that will be running ABR and driving both a desktop view and a VIS head-mounted system. I do all my real work on the Mac and just use the Windows system to host ABR. Let's see how. Back in the pipeline browser, we add an additional filter to each of the three pipelines that produce derived data. In the property page for each of these, we tell it where to send the data, here the IP address of the Windows box. I'm sure I could do this by host name if my home network was set up properly, but this is easy. We also give the data objects a name, analogous to the file names we used earlier. When we run the visualization in Paraview, the objects will be transferred from Paraview on the Mac to ABR on Windows and installed in ABR using the given names. And there they are in the ABR GUI on the Mac display, and the results show up in ABR without interacting with the Windows system at all, other than running ABR to begin with. And the best part is that the connection persists between Paraview and ABR. Recall that this data was a time series. If we hit play on Paraview, it will iterate through the time steps, produce derived data sets for each time step, and send them to ABR. ABR receives them, and in a time step synchronous fashion, updates the visualization. Here we see the ABR display as Paraview iteratively loads in a time step, derives the renderable data objects, and transfers them to ABR. ABR understands that the data is updated, and when all data products for a time step have been received, updates the display. Note that until that point, ABR remains actively rendering the prior time step, giving the user the effect of smooth motion, periodically updated with new data. In summary, we have shown that the basic input format for scientific data into ABR is the VTK unstructured grid object format and how it can be loaded into ABR either manually from saved files or received directly from Paraview, which can be running anywhere, firewalls permitting. We have driven ABR directly from the TAC supercomputers in this manner. And with that, I'll call for questions. Thank you.